everything is j omega. Now I want to get rid of all of those coefficients. Now this one is still fine, but everything else, I don't want it. What should I do? What is the procedure? To get from that thing to something times j omega divided by something plus 1, j omega divided by something plus 1, divided by j omega divided by something plus 1, and the same thing here. Because this is what I want. Now, how I find that something each time, and what is the procedure? Because I want to isolate each one of those and to pose them separate, and then to add them together.
Divide out the 5. Or divide out the 6, divide out the 1, divide out 2.
Exactly. So I basically need to divide and multiply by the same number each time. Which means I want to get rid of that 5, for example. So it was 3 here, right?
So you just take out
it was 3 here. And I will divide by 5 and multiply by 5. I have to write it here. I need to divide by 5, so I will have j omega divided by 5, right? And I need to multiply by 5. Haven't changed anything yet, right? But then I have this shape I want. Now, here I need to divide by 6, both of those, and then to multiply by 6 to keep it right. The same thing here. So I need to divide by 1, multiply by 1, it doesn't matter, so it still will be 1. Here I'm doing the same thing with 2, and then I need to multiply by 2 here, which will come here to the coefficient, and the same thing here, dividing by 3, multiplying by 3. Something like that. Okay? So I will have coefficient, which is sitting here, which is the overall gain of the system, like where it starts, essentially. So then I need just to find 20 log of that number. This will be the starting point from the left, right? And all of the magnitudes of those, like total magnitude where it starts at omega 0, will be 1, always. Which means 0 will be. So they will not affect at all the Bode diagram sheet, up or down, right? Because they all starting from 0. All of those. Do you see why? Because magnitude of each one of them is 1. Okay.
You did the other way, you have to add a bunch of them together to figure out
Now, what is great thing about Bode diagrams and why he developed it that way? Because look, if you have phases of separate zeros or separate poles, in complex domain, phases just adding together. Like if you have multiplication of zeros, for example, you just add the angles, which is basically adding the actual plots. If you have division, you're subtracting the plots, right? This is how angles work. So you have exponent of j theta times exponent of j other theta, so you're just adding them. If you're dividing by exponent of j other theta, then you're just taking theta 1 minus theta 2, right? This is what you do. You're subtracting or adding different things. Now, what is basically subtracting angle? It's just adding negative angle. And this is why some Bode diagrams in phase go down and some go up. It's just addition with negative angle. That's it. This is the overall idea. So those plots are not really different. For the phase, it doesn't matter if your angle is positive or negative. They just separated that into 2 types of plots. Some go up, some go down. Depends if you're dividing by that angle, by that polynomial, or multiplying by that polynomial. This is why they have up and down, because it's just subtraction of the angle. But in Bode diagram, you're always adding. Sometimes you're adding positive angles, sometimes you're adding negative angles. That's it. This is the difference. Now, for amplitude, which is here, okay, why are we using log? Why are we using decibel here? It's the same reason. We don't like to multiply graphical plots. It's too difficult. You cannot take one plot and then point by point multiply it by another plot, at least in your head. And now with simulation probably you can, but in MATLAB obviously you can multiply them point by point. But in 45 it was not possible to do that, and computers were not available frequently. So the idea was that in log, like log of multiplication is basically sum of logs, right? So you can graphically add two graphs together. So you're taking one pole graph, which looks like that, another pole graph, which looks like that, just add them point by point. Adding point by point is easy, right? Much easier than multiplication of point by point. And this is why they used log scale, because in log, multiplication becomes addition. And this is the entire idea of Bode diagrams. Now, I want to show you some more complicated example where we'll see more details on that, how you actually use it. Obviously, in the test, you will not have to plot Bode diagrams of that kind. It's too time consuming, but you will see the process. And again, the importance of Bode diagrams is not really in asymptotic diagrams, because nobody really plots asymptotic diagrams today. You can use computer for that, right? So it's not really useful for that purpose. It's useful for system identification, where you have black box, you send into the black box all kind of sinusoidal inputs, measuring sinusoidal outputs, you want to know what is inside of the box. Based on plotting point by point those Bode diagrams, converting them to asymptotic domain where you know where those breaking points are, and from that you learn what the system is. Okay? Now, so we have another example. We want to plot Bode diagram of G of S, which is S plus 30, S plus 1, S plus 7, S plus 100, something of that kind. Okay, so what is step number one? We want to identify, let's plot first of all the gain. And the gain will be like that, so we need more space. So this will be log omega. This will be G omega at set value in dB, which is log scale. So this is 0 dB. And now, where it starts? What is the initial point it starts with?
We normalize it first?
You can normalize it that way, so you can write it that way. So what will be Z coefficient, basically?
We divide by 700.
Essentially, can you think how you get the coefficient without doing all of that manipulation?
Yeah.
Like now you know why you need that coefficient specifically to start with, but can you get that number without having all of that? So what are those things?
30s on top, 700.
Yeah, so 30 divided by 700, essentially. So it's 3 divided by 7. So you will start with some point. This point will be obviously 20 log 7 over 7, not 7, 3 over 7. Okay, so this will be some point. Will it be positive, negative?
Could be negative.
Should be negative, because this one is smaller than 1. So log of 1 is 0, so everything which is smaller than 1 gives you obviously log which is negative. So it will start somewhere, okay? And now we need breaking points. Let's say we have something like that. Let's say this one is 1, 10, 100, 1,000. Okay, so let's identify where the breaking points are. First of all, we have breaking point at 1. Let's put it here. Just marker for change. 7, so 7, I guess it will be somewhere here, close to 10. 100, which is here. And then also 30. So 30, it's somewhere in the middle. So it's obviously farther, maybe probably even farther here, more than a half. Okay, so this is 1, 7, 30, and 100. So those are breaking points that we have here. Now, how we start to plot? Before the first breaking point, nothing happens in asymptotic Bode diagrams. So we're starting with flat plot, and this flat plot will be starting from here and going up to 1. The same value. Okay, so here you will have some breaking point. Now, the breaking point will go up or down, depends if it is pole or 0, obviously. You can use the tables that I showed you to see if it goes up or down. So poles going down and zeros are going obviously up. Now, each one of them will contribute plus or minus 20 dp per decade. Now, so first one is basically s plus 1, right? So where it will go?
Minus 20 there.
That defines the boundaries where it will change. And nothing will happen in other intervals. So, first of all, between 1 and 7, it will be the same mode, right? It will not change. It will not be different between 1 and 7. So it will go down with minus 20. Right? Minus 20 dB to E8. And at 7 it will change. How it will change?
It'll go down to minus 40.
So now it becomes minus 40. So it starts to be minus 40. Until it gets to 30, which is the next one. I mean, I'm basically sorting poles and zeros on that plot. So after it becomes minus 40, it goes and nothing changes until we get to 30.
Back up to minus 20.
Now, at 30, you have basically another change, which is 0 now. And what will happen to 0? It will go up. But how much it will go up?
20.
It will go up 20, which is added to that minus 40, which will be back to minus 20. Right? So it will get back to the same that was before. And now at 100, it will change again. Right? So it will just go down again with minus 40. Forever. Any questions on that? So this is how magnitude looks like of that plot. If you plot that in MATLAB, it will look probably something like that. It will go make something down, and kind of a little bit more down. Something like that. This will be the realistic plot. We'll go between those points. But the asymptotic plot looks like that, which is approximation of real plot that you can plot by hand. Any questions on that? Okay, phase is much more complicated actually to plot, because in phase we need to plot starting with the point which is 10 times less than the pole and then 10 times more than the pole, which is kind of very tricky thing to do. Okay, so let's plot some phase. This is low omega, and this is angle H, equals G. Okay, now let's put here 1, 10, 100, 1000. But now we need also that thing divided by 10 and multiplied by 10. So we need to have 0.1, and we need to have, basically it will be not longer than 1000, but let's make it 10,000. Okay, now critical points. This is the most tricky part here. So first critical point will be from pole at 1. So it will be 1 divided by 10 and 1 multiplied by 10. So starting with 1, and then you have critical point here, which is 0.1, pole, and 10 pole. Okay, and just denoting that with P and Z just to make sure that we remember which one produced those points. Because otherwise it's becoming very tricky very soon.
We're multiplying what by 10, each pole and each zero?
Each pole and each zero location we're multiplying and dividing by 10. And those will be breaking points because if you look like that. So let's say you have some sort of phase which is going like that.
Correct.
Okay, so your location of your pole will be here.
Okay.
And this will be P divided by 10. And this will be P times 10.
Okay.
So you need those breaking points. So now breaking point is not at P, but it's like P divided by 10 and P multiplied by 10. It's also the breaking points for poles and zeros, for phase. Okay, because phase looks like that, it goes that way. It's like a tangent function, right? So we saw already before that this is a tangent function which is looking like that. So the middle part of the tangent is exactly the location of the pole. So we need to start 10 times lower than that and to finish 10 times after that, okay?
And
No.
are we still using 1 as a pole as well, or strictly just the divided 10?
This is only for phase.
Right, that's what I'm saying.
Yes.
Okay.
So you're using, before that point nothing happens, so it's flat
Right.
before that. And then after that point nothing happened for that plot, for that first pole,
Right.
right? But something might happen for the second or third one.
Well, that's what I
So
was,
they might overlap.
that's what I was asking, is on the graph where you had the P marking, you wanted to divide it by 10, multiply by 10.
Yes.
And we're no longer using the
You're no
1.
longer using P at all.
Okay,
So P, you don't care about P. Like nothing happens at 1.
right.
It will have just some single slope if nothing else happens in between. Now, second one is 7, which is 0.7. Let's say here, 0.7 pole, right, and 70, which is here. Third one is 30, which is 0. So 30 will be 0.3. Let's say somewhere here. 0.
Wouldn't it be 3?
Yes, because not here. It will be 3. Three will be 0. Okay, and 30 will be 0. 300. Not here again, 300. 0. Okay, and the last one is 10. So here we have 10 pole and 1000 pole.
So 2
Okay, now we get to the nightmare part.
No.
Where it starts? Let's start with simple questions. Where it starts? What is the angle where omega equals to 0? It starts with 0 angle. Why?
Because it's 0 over 1.
So what are the two options that you have? You have 0 and you have what other option?
Negative pi over
What angle it could start from?
negative pi.
No, it could be negative pi
Negative pi. So minus 180.
or positive pi, which is the same thing, obviously. Like, why is that? y could be
Because
negative
when
pi
you
over.
plug in 0, you get a positive number.
Yeah, so if you
If
get
a
positive
negative
number, you
number,
have zero angle. If you have negative number, this number is pi angle,
Yeah.
or 180, or plus minus 180, whatever is the same, right? In that case, if you put in s equals to 0, which is j omega equals to 0, you get some positive number, which is 30 divided by 1, 7, 100, and so on, it's all positive. So you get some positive, which means zero angle. So until that point, nothing happens. Green. So until 0, 1, nothing happens. Now, after that, it goes down, right? And now let's put all those lines together where it's changing behavior. Something of that kind. So we identify that it should start here, and then it should go up or down.
down by 20 decibels.
So it goes down. And if it would get to that thing, how many you have here?
Minus 90?
Minus 9. So single pole can add 90 degrees, which is by half, right? But it's not getting there because you have another pole here, right? So what happens with that pole now?
Because another plus or minus 90?
So it goes with more down until it gets to third 0, right?
Yeah.
And then it goes a little bit up,
Wait, the 3 is 0, right? So it's true.
so it goes the other way.
Yeah.
Right.
Yeah, poles are down or decreasing in slope, and or not decreasing in slope, but getting more negative.
Yes, more negative.
Yeah.
Okay, and now at 10 you have double pole, but one is ending, right, from this one, and one is just starting. What it means. So in one it's like going again up, and another is going down. What it will do? No change.
Wait, what?
They will cancel each other.
The 2 tens?
Uh-huh.
I thought they were both poles, right?
No, this is
Well,
one looks like
it
that.
depends on whether or not
One
it's the
goes
beginning
like
or
that.
the end of a pole.
Up to here, then it goes down, and then it goes like that. And second one goes like that. So it starts here, right, and going, starts here, and then going down, and then up, right? So this one, the first one, actually gets up from that point.
Okay.
And that one starts to go down, which means it's kind of continuation of that thing. If you add in those two, you get just the same thing going down. Okay, now 70 is basically done with that one, so it's ending interval of that 70, of that 7, right?
Right.
Which means it should go up.
Okay.
Now 300 is 0, which is going even higher, right?
Right.
So it probably will be kind of flat. And then you have
The end.
pole, which is ending up
pole. So it's gonna go up.
here and go somewhere. Now, where it will be? What is that point?
Minus 5 over 2.
How many degrees? Pi over 2?
Minus 90 degrees.
No. How do you know what it should be? Basically look at the transfer function. How many poles and how many zeros you have. So each pole adds 90 degrees and each zero removes 90 degrees total.
So it's minus 180.
It's minus 180.
So each, okay. So minus 90, minus 90, minus 90.
Yes, exactly. So it's 3 poles adding 90 degrees, so it's 3 times 90, and 1 zero subtracting 90 degrees, which is plus 1, 90 degrees.
So each left pole we have is adding the decreasing for a pole, well, then each
Yes.
right side is adding, and it's the opposite.
Yes. So you can basically, for simplicity, maybe you should write like this one is ending, this one is subtract.
Or opposite.
Yes.